Welcome to the AP Physics lecture. This is going to be covering the law of motion. Here, dynamics. We're covering here friction. Friction. If you take a look, this is at a molecular level. These are like the atoms that are interacting on a surface on a classical level. Okay. So these is the atom structure. Okay. Is going against the atom of the surface atoms here, and this is your object's atoms. All right, think about that. The roughness of one object surface colliding with the roughness of the other object surface. Friction is the sum of all the microscopic collision due to the imperfection in each surface. Each surface has imperfections based on their molecular distribution. The variables that we use for force of friction, you might see it as the squiggly F, or you might see it as the force of friction. That's what the F is. So you could write it either ways. There are two types of frictions that we work here. We work with static friction, which is going to be F of S, which is on a stationary object, and if the object is moving, we call it kinetic friction, F of K. In this picture here, you're going to see the force going to the right is the force applied, and there's a force holding going against it, which is the squiggly F, which stands for friction. In order for static friction to be present, all the forces and the components of the force parallel to the surface must create a net force, excluding friction, that is attempting to move this object. In this scenario, the object does not move because the force forward to the right is equal to the force holding it back, which is the force of friction that is going left. This object does not move. It remains stationary. It's at equilibrium. Static friction is the strongest form of friction. When the object is at rest on the surface, it is thought that the imperfections in the surface sink in towards each other, locking the surface together. In order to move the object, you must increase the magnitude of the forward force, that's the red F, to the right until it is strong enough or significant enough to push the object out of its locked condition. That's why we say the force of static friction is larger than the force of, that's why we say that the static friction is larger than the kinetic friction. Kinetic friction, you see how the interlock gets out, the object's already moving here. An object begins to move, the kinetic friction now replaces the static friction. It still is in contact. You see there's the bumps right here, or still bumping on the surface, right? Okay, but there's less contact with the surface, okay, but there's still contact. And we call this the kinetic friction, the collision or the touching of the object when the object is moving. The kinetic friction is weaker, and the magnitude of the friction force decreases it. Why? Because you see how there's less surfaces that is touching. There's only, in this picture, there's only two surfaces. Okay, this one doesn't touch. While as before, look, you see there was a lot of touching. 2, 3, 4, 5, right? There was a lot of touching. Okay, less touching. As the object begins to move, kinetic friction does replace the static friction. The kinetic friction is weaker, and the magnitude of the force of friction decreases. In this diagram above, the force applied forward to the right is greater than the force of friction, which is to the left. The object would now accelerate. Look at the arrows. You see there's more arrows going to the right, so the object's going to move. To move the object at a constant velocity, you would actually, now right here, you would have to, for it to move in constant velocity now, for it to have not an acceleration, you would have to cut off the force of friction to make it smaller, something like this. So it balances out the force of friction. Okay, that's what it says here. You would need to reduce the forward force until it is at equilibrium with the force of friction, same magnitude. The applied force needs to keep the object moving at a constant velocity would be smaller than the force needed to start the object moving in its first place. Force of friction. There's two parts to the calculation. First of all, there's something called a mu. The mu is the coefficient of friction. This reflects how rough the surface are, the imperfections in the molecule's surface. The higher the coefficient, the stickier the surface are to each other, and the stronger the friction force will be. The coefficients have no units. On below, I give you a diagram of some mu's that you will see, and you will see wood on wood is the highest at 0.4. Then you will have ice on ice, which is 0.1. When we talk about ice in our class, we mostly treat it as like almost approximately frictionless. Okay. Notice that the static friction here, mu s, is always larger than the mu k, because again, that's because static friction, the object has more surface area to interlock with the other molecules, the other parts. So again, mu s, that stands for the mu of static friction. That's the mu of k, which is the coefficient of kinetic friction. And really important is the normal force, because again, we talk about how the force of friction is when the molecules are touching each other, touching the surface. As a result of them pressing against each other, their normal force is going to be there. Okay, these are all the components parts of the force of friction. I'm going to show you now the calculation. So the force of friction for kinetic friction is going to be an inequality right here. This is an inequality. Okay, but when it is a kinetic, it's only one value, so it's equal to. This is why you can solve it. In short, if you want to think about friction, people think friction is fun. Friction is fun, mu, n. So do you see how it looks like the word fun, right? This is why they call friction mu normal force, right? So this is in its case, but please understand that when it's kinetic friction, it's an equation, and inequality, it's equal to. But if it's an inequality when it is static friction, you're going to see this when we do the calculations in the next part. Here's some sample problems for the static friction. A 2.0 kilogram block is initially at rest on a rough horizontal surface with a coefficient of friction mu s equals to 0.2 and the kinetic friction 0.1. What is the force of friction? When the equation for static friction is set as a equality, it can only be solved for the value of the maximum static friction. Remember, we said it. We can only solve if it's an equal sign, and we only could do that when we do the maximum. Okay, so we would say that F, force of friction, static maximum, is equal to mu s times n. There you go. That's 4 newtons. Okay, the 0.2 is the coefficient of friction. The 2 is the mass. The 10 is gravity. However, when an object is at rest, the actual magnitude of the static friction may be less than its maximum. Okay, that makes sense because it goes towards the maximum. We cannot solve an inequality. So how is static friction determined when its magnitude is less than the value of static friction? Well, when an applied forward force F attempts to move an object forward along a rough surface, the force of friction minus F opposes the forward. So what we could say is that if the opposite is initially at rest, the magnitude of the applied force is less than the magnitude of the maximum static friction. Then the object can't move because here's the picture, because F forward is more than F to the right is less than minus F right here. The object can't move. Okay? The object remains at rest due to static friction, so it can't really move. Even so, let me show you. It's going to make more sense once we do the graph, right? So here we saw this is force of friction, right? So let's say we applied a small force like F here. Does it move? So we don't know it. What about if we increase it? We still don't know. It's still not moving until it reaches the same length, right? Its maximum. Then we could figure it out. Okay? That's what it means here. To summarize, there are three possibilities for static friction problems. You will see it here about the inequality. And again, this can't be solved. The best you could do is solve for its maximum, the maximum static friction. Understand that the maximum static friction, in this case, you could then find the force of applied forward. Now, we're going to talk about the graph that it interacts with. We talk about this tipping point here. This tipping point is considered the maximum, right? Before the maximum, the forces that is being applied increasing, but the object's still not moving. There's no motion during the first part of the graph. Once it reaches the maximum at 40, then it drops down as a piecewise function. Then it has its kinetic friction. This object is now sliding. Two things that you need to understand is that the applied force Fa has to increase in its magnitude. Right here, you see how it's increasing to the point that it overcomes the force of static friction. So if you think about this in terms of the free body diagram, think about the force of friction here, which is going to be 40 newtons. Okay, then let's say you apply 10 newtons forward, the object won't move. Now you apply another 10, so it's 20 newtons, the object won't move. That's now you say you applied 30 newtons, the object isn't moved until you apply 40 newtons. Okay, now the object's going to move. Right? The force of kinetic friction is less than the force of static friction. So that's what they mean here. Do you see how this is 40? The force of friction is below it. So now I'm going to show you it in a little bit more detailed graph. And a hypothetical experiment of an applied force will be varied. So we start off from our last problem here. We saw that we did the calculation. So the maximum of the force of friction is going to be Fs max. We think about that as the horizontal asymptote. Now we're going to start applying a force. Let's say we applied force of 0. Nothing happens. We apply a normal force of 1. Doesn't happen. We apply normal force of 2. Doesn't happen. We apply normal force of 3. Doesn't happen. Until we reach the top. Okay? As of right now, the force of friction is stronger than anything else, than the applied force. It is to the point where you apply the 4 Newton force, which is its maximum. At 4 newtons here, right, the force forward is equal to the force back, right? The forward force is equal to the force of friction, which is pulling it back. The object doesn't move, though. Please understand, the object is still at equilibrium, because here, this technically is still balanced. Okay? For it to overcome, right, we have to increase the applied force very slowly to the point that it becomes like 4.001 newtons. Once it becomes slightly above 4 newtons, we will see then the object will start moving. Okay? Then it jumps to a piecewise function, because once it overcomes static friction, it drops into here the kinetic part, because it drops to a new value. The reason why is because we have to plug in a new value here for mu k. So you will see that the kinetic friction here is going to be smaller because the mu is smaller. All right. So now the forward force can be less to move the object. Important things to understand is that the equation always you can solve for an equation that has the kinetic friction. However, the value of the coefficient of friction is different. The kinetic friction is weaker than static friction. As long as the applied forward force is greater than 4 newtons, the magnitude of the kinetic friction will remain constant. In this example, the kinetic friction is 2 newtons. So what about constant velocity? Well, constant velocity is an important case, right? It is still This is when the forward force to the right is equal to force of friction, kinetic. Same thing here. It's just 2 newtons. You're only looking at the essentially just the blue part here. You're only looking at the blue part. This is the 2 newton, and this is when it's moving, right? That's the kinetic part. So we can plot that at the constant velocity at 2 newtons. To summarize, the friction is summarized in this graph. This is stationary. The force here, we saw that the forward force is less than the friction force, static. You can't solve this, but we know it's still less than maximum though. We could see we can solve for it if we take it to be the maximum value. This is when the forward force is equal to the maximum of the static friction force. At constant velocity, okay, well, then we talk about acceleration. You can't solve for it, but you can solve for the force of friction kinetic though. And then constant velocity is right there where it's like the same value as the accelerating part. Good. So there you go. Those are an introduction to friction and on a basic level. Okay.